Gathering precision data about a mountain range or forest presents a fundamental challenge. We must measure these targets without ever touching them. We solve this through remote sensing, the science of measuring a target's properties from a distance, typically using instruments mounted on high-altitude aircraft or orbiting satellites. Remote sensors operate as highly calibrated instruments designed to detect and record electromagnetic radiation, energy either reflected or emitted by the objects below. This diagram outlines the remote sensing process. Energy from the sun travels through the atmosphere, striking a ground target. Reflected energy bounces back to an orbiting satellite sensor. The sensor transmits this data to Earth stations, where analysts extract usable information. Mapping ocean depths or forest health from hundreds of miles away requires this rigorous understanding of the physical journey that energy takes. That energy takes the form of electromagnetic radiation, which propagates through space as oscillating waves. These waves result from the oscillation of two interdependent forces, an electric field and a magnetic field, moving perpendicular to one another. We measure these waves using two core parameters. Wavelength is the physical distance between two successive crests, while frequency counts the number of wave cycles that pass a point every second. Regardless of their wavelength, all electromagnetic waves travel at a constant velocity, the speed of light, or approximately 3 × 10⁸ meters per second. The electromagnetic spectrum classifies all radiation based on these varying wavelengths. By isolating specific bands, we can tune our sensors to detect different physical realities. Instruments tuned to the visible band, between 0.4 and 0.7 micrometers, detect the colors and textures perceivable by human eyes. Moving outside this range allows us to see the invisible. The near-infrared band tracks vegetation health. Thermal infrared measures heat emitted by objects, and microwave bands have wavelengths long enough to penetrate thick cloud cover. The spectrum functions as a menu of specialized probes, allowing scientists to select the exact wavelength needed to extract a target's physical properties. Before reaching the ground, energy must pass through the atmosphere. Atmospheric particles scatter the incoming radiation, altering its path and intensity and introducing noise into the data. Furthermore, atmospheric gases like water vapor and carbon dioxide absorb specific wavelengths entirely, effectively blocking them from ever reaching the sensor. When the incoming radiation, labeled I, finally strikes a target, 3 primary physical interactions dictate the returning signal. Absorption occurs when the target converts radiation into heat based on its chemical properties. Darker objects typically absorb more energy than lighter-colored ones. Transmission occurs when radiation penetrates the material. This is a critical interaction for sensors designed to observe subsurface features in water bodies. Finally, reflection is the portion of energy that bounces back toward the sensor. The characteristics of this reflection determine what the instrument actually sees. The type of reflection depends heavily on the physical roughness of the target surface. Specular reflection occurs on smooth surfaces like water or pavement. The energy bounces away in a single direction, meaning it often misses the satellite sensor entirely. Diffuse reflection occurs on rough surfaces like vegetation. The energy scatters in multiple directions, ensuring that at least some radiation reaches the sensor. Without the scattering effect of diffuse reflection and the existence of atmospheric windows, no usable data would ever return to space. Every remote sensing mission must account for the initial source of this electromagnetic energy. Passive remote sensing systems rely entirely on naturally available energy, primarily sunlight that reflects off the Earth's surface. These systems are constrained by nature. They are restricted to daylight hours, and their optical sensors cannot see through heavy cloud cover or adverse weather. Active remote sensing systems overcome these limits by generating and emitting their own focused pulses of electromagnetic energy. By acting as their own energy source, active systems like radar operate at night. When using microwave bands, they can penetrate directly through clouds and dense vegetation. This independence requires immense onboard power and highly complex data processing to handle the returning backscattering energy. Mission design is always a compromise between the cost-effectiveness of natural sunlight and the penetrative power of an active sensor. Once the signal reaches the satellite, its utility is defined by 4 distinct limits of resolution. Spatial resolution determines the smallest ground unit the sensor can distinguish. Higher spatial resolution provides finer details by utilizing smaller pixel sizes. Spectral resolution is the sensor's ability to slice the electromagnetic spectrum into discrete, narrow bands to isolate specific information. Radiometric resolution measures the sensor's sensitivity to minute differences in energy intensity. An 11-bit system provides more detailed information than an 8-bit system by recording over 2,000 distinct levels of intensity. Temporal resolution refers to the revisit rate, how frequently the satellite passes over the exact same coordinate to monitor physical changes over time. The utility of an Earth observation dataset resides in a meticulously engineered balance of these 4 resolutions. We see the synthesis of active architecture and wave physics in LiDAR, light detection and ranging. As an active system, an airborne LiDAR platform fires a rapid barrage of laser pulses toward the target area below. These systems utilize specific wavelengths, often near-infrared for terrestrial topography, or green lasers for bathymetry, which can penetrate water. The system calculates distance by measuring the precise time of flight of the laser pulse. This relies on a core equation. Distance equals the speed of light multiplied by time divided by 2. The measurement depends on the rough target's diffuse reflection, scattering a fraction of energy directly back to the sensor. While airborne systems prioritize broad coverage, terrestrial LiDAR units are mounted on tripods or vehicles to achieve hyper-accurate mapping of smaller, complex structures. LiDAR represents the successful integration of active pulse emission, specific band selection, and extreme spatial resolution. Remote sensing scales the physics of a single wave of light into comprehensive global datasets. By calculating exactly how radiation interacts with matter, scientists construct highly accurate digital representations of our physical world.